Hello everyone, today we'll talk about the solution to the problem cousins in binary tree 2. This problem defines cousins as nodes that have the same depth in the tree but different parents from a given node. And so the brute force solution to this problem will probably be O of n squared. It will probably be a quadratic because for every node we have to, if we're naive, traverse the whole tree to find all its cousins. And the reason for it is that we want the sum of all the cousins values, and in particular there can be a lot of cousins that are far away in the tree. So if we have even a full binary tree, then the whole bottom level, almost all the nodes are cousins, and in some cases you would have to go up the whole tree, then down to a cousin. So yeah, this would be a quadratic solution. And there is a very common pattern. I'm not sure if it even makes sense to call it a pattern because it's very simple. But here we have to adjust the value with the sum of all the cousins, of all the nodes on the same level with different parents. And as is very typical, especially in problems from probability theory, whenever you want to calculate some value and there is some notion of complementarity, which in probability is that when you're calculating the probability of some event, then the sum of the probability of that event happening and not happening is typically 100%, right? So again here, we have the complementarity in that we can either sum the values of all the nodes at the same depth with different parents, or assuming that we have access to the sum of all the values of the nodes on a given level, then we can take the sum of the whole level and subtract all the nodes that are not cousins. The nodes that are not cousins in this case are nodes that have the same parent. And there aren't too many nodes like this. I mean, at most 2 nodes can share a parent. So in other words, we'll have to go and make 2 traversals for the tree. The first traversal, which is very similar to what we had in yesterday's daily, we calculate level sums. So this is very simple recursive function. If you want, you can look at yesterday's video to see it in action in a problem that was more focused on level sums. And after that, in sums, we have the sum of values for all the nodes at a given level. And now, however you want to traverse the tree now to update the results is up to you. One way of doing that would be to have a function that, again, will remember the level, will remember the node, and will also remember how much we have to subtract from the value of a given node, and that function will be responsible for recursing and for updating the values in the nodes. So at first we start at root, and we have to subtract from it the value of the root. And now, again, if the node doesn't exist, the same thing as in this recursive function, so this is the base case, we just don't do anything. Otherwise, the value of our node becomes the sum of the values on its level minus this thing that we have to subtract. And now we have to recurse. We go one level deeper to the left and right nodes. And we have to subtract something from their values. Notice, of course, that the values of both our children will be equal by this definition of cousins. And the thing that we have to subtract is, of course, their original values. So the value for left and right, of course, if they exist, otherwise 0, the sum of that is what we have to subtract. And this is the whole solution. We calculate level sums, we replace the values by subtracting appropriate values from the level sums, and we return the modified tree because we've modified it in place.